Hello, my name is Gayana Vardayan, and today I will present our work titled On the Analysis of a Multipartite Entanglement Distribution Switch, done in collaboration with Philippe Na, Sekar Guha, and Don Towsley. In this talk, we will examine a simple distributed quantum system. Distributed quantum systems have many uses, and these can be broadly divided into three categories: cryptography, which includes quantum key distribution; scientific applications, including high-precision clock synchronization and baseline imaging; and distributed quantum computation. In general, quantum communication offers functionality that's not achievable classically, and this is often achieved by exploiting the properties of entangled quantum states. The rest of the talk is organized as follows. First, I will give you a brief introduction to quantum computation and communication. Next, I'll introduce the problem, which involves a quantum device called a quantum switch. In this section, I'll describe the operation of the device and discuss the problem, analysis, and results. Finally, I'll conclude with a summary and future directions. Now, on to a brief introduction. A qubit is the quantum analog of a bit and can be represented by a two-level quantum mechanical system such as photon polarization or electron spin. These states can be represented using Dirac notation as shown here. For example, an electron with spin up can be mapped to state 0 and with spin down to state 1. Unlike a bit, a qubit can be in a superposition of states as shown here. Here, alpha and beta have a probabilistic interpretation and their magnitude squared must sum to 1. Two or more qubits are said to be entangled when the state of one cannot be described independently from the state of the others. One type of entangled state is known as a Bell pair or state and is the single most important resource for quantum communication. This is a two-qubit state where the two qubits A and B may be separated by an arbitrary distance. Even in this case, if we measure qubit A and get 0 as a result, then we know with certainty that qubit B is also in state 0, and similarly if we measure one of the qubits to be in state 1. Let us now look at an example of a quantum distributed task. We will look at one iteration of the E91 protocol, which is an entanglement-based quantum key distribution protocol. The goal for the users is to create a one-time pad, which is the only provably secure means of encryption. To do this, they use a quantum network to generate a Bell pair. One qubit is given to Alice and the other to Bob. Next, the users randomly choose one of a set of different measurements to perform on their qubits. If, for instance, they both choose the computational basis for their measurements, then they will both obtain result 0 with probability 1/2 or result 1 with probability 1/2, hence generating a raw secret qubit. But had they chosen different bases to measure in, their results would be uncorrelated. Alice and Bob repeat this process until they have generated enough raw secret qubits to be distilled into a usable one-time pad. A unique feature of these types of protocols is that even in the presence of an all-powerful adversary, Alice and Bob can use sensitive statistical methods to detect eavesdropping. There are many such promising and exciting distributed quantum system applications, but they do come with challenges. One of the most significant challenges in quantum communication is transporting a quantum state over a long distance. A qubit can either get lost or altered in an undesirable way while in transit. In general, for a fiber optical link, the probability that the photon reaches the receiver depends on the link's transmissivity, which is given by the function e to the minus alpha L, where alpha is the fiber's attenuation coefficient and L is its length. Clearly, a longer channel means higher loss probability. One method of dealing with losses in a classical network is to use repeaters, which take in, as an input, weak, distorted, or noisy signals, and generate clean and strong signals. On a quantum channel, such an operation is prohibited. That is, one may not take an arbitrary or a non-quantum state and create an independent copy of it. This is a result that is fundamental in quantum mechanics and is known as the no-cloning theorem. So how can we help Alice and Bob transport quantum states to each other? We can create a simple quantum network by positioning a device between them known as a quantum repeater. The users will generate entanglement between themselves and the device, and these link-level entangled states are Bell pairs that we saw in previous slides. The repeater will then perform some local operations and a measurement, collectively known as a swapping operation, the result of which is a longer distance bell pair directly entangling the user's qubits. This new bell pair can now be used as a resource, for example, to teleport a quantum state or to generate a raw secret qubit in entanglement-based quantum key distribution. Note that due to non-idealities within the quantum repeater, the swapping operation may fail. Also, to generate the elementary link-level bell pairs, we must still send photons between the users and the repeater, which means that the probability of successfully generating these states still depends on the link's transmissivities. In this work, we will discuss how these phenomena may be modeled. In previous slides, we saw that a quantum repeater can connect two bell pairs into a longer distance bell pair. But this operation can be generalized to entangle more than two users. For instance, a GHZ projective measurement can be performed to entangle 3 or more users and generate an N-partite GHZ state, where N is the number of qubits. These states have many uses, which include multiparty quantum key distribution, quantum secret sharing, quantum sensing, and multipartite generalization of superdense coding. N-partite GHZ states are the focus of our work. Future quantum networks will consist of many quantum repeaters whose objective will be to provide entangled states to sets of users who request them. Such networks will support applications such as quantum key distribution or will be used to improve sensing. Since each device may be connected to many other devices and users, it's reasonable to assume that the devices will be equipped with entanglement switching logic. Hence, from now on, we use the term quantum switch instead of repeater. Some questions that are natural to ask about a quantum network are, what's the capacity of such a network, and how many qubits will be needed at a quantum switch? The goal of our work is to make an initial effort in answering both of these questions for a simple quantum network. To answer these questions, consider how such a network may operate. The first step will be for the links to attempt bell pair generation. Naturally, not all the links will succeed, but if enough of them do, the quantum switches will perform the necessary swapping operations to generate an end-to-end entanglement. In this example, the result is a tripartite GHZ state. This is the basic idea behind entanglement switching, which brings us to our problem. Regardless of the application that the quantum network is being used to support, the network must be able to generate and distribute entanglement efficiently. To gain insight on how this can be done, we focus on a single quantum switch, and our goal is to determine stability conditions for its operation, derive its capacity, and also an expression for its quantum memory occupancy. In this work, we constrain the switch to serve N-partite GHZ states for N greater than or equal to 2. We will perform the analysis using a queuing theoretic approach. It's worth noting that our problem formulation is useful for many other applications beyond entanglement switching. In general, a quantum switch can be thought of as a stochastic assembly-like queuing system whose job it is to wait for items to arrive at the central node, to be assembled into composite items, and subsequently leave the system. Prior work often approaches such problems by approximating or bounding the capacity of such systems, but exact analyses are rare. Also, problem formulations that we found in literature are sufficiently different from the one considered in this work, so as not to be extendable to our problem. Before we analyze the quantum switch, let us describe its operation in more detail. First, since we are interested in the performance of the switch, it's reasonable to assume that the endpoints are quantum-equipped users with infinite and noiseless quantum memories. This will ensure that the endpoints do not limit the performance. Next, the switch is also equipped with quantum memories. In this work, we will focus on a simple problem formulation wherein the memories at the switch are also infinite and noiseless. In the graphic, gray circles are for unoccupied and red are for occupied quantum memories. Finally, the switch can perform projective measurements and will be capable of classical communication. The switch will serve k users, and its operation consists of 2 steps. The first step is bell pair generation over the individual links, and the second step is N-partite GHZ state generation via swapping operations. We will model the link-level entanglement generation as a Poisson process with parameter mu representing the rate of successful entanglement generation at the link level. We assume that all links are identical so that they all generate bell pairs at the same rate. The second step involves entanglement swapping based on user demands or a switching policy. Let's examine that in more detail. At any time, the switch has 3 options: perform a swapping operation, store the qubit in memory, or wait. Suppose a link successfully generates a new bell pair. If there are not yet enough bell pairs for a swap, the switch should store the qubit from the newly generated entanglement in memory. Later, suppose that another link successfully generates a bell pair, and perhaps the 3 users with bell pairs wish to share an entangled state. Then the switch may perform a GHZ projective measurement and entangle their qubits. It's worth noting that successfully generated quantum states are sometimes not what they ought to be. Fidelity is a measure of closeness of a quantum state to the desired quantum state. In this work, we assume that all quantum states have unit fidelity to corresponding ideal pure states. We can now move on to the analysis portion. If the system we have just described is in steady state, then we define its capacity C to be the number of end-to-end entangled states generated per time unit. We denote the number of stored qubits at the switch with E of Q. Since we're interested in the capacity of the switch, which is the maximum rate of entanglement switching, we must assume that any set of end users wish to share an entangled state, as an arbitrary switching policy would likely fall below the capacity of the system. For the same reason, we will assume that bell pairs will be used in entangling measurements as soon as there are enough to generate an n-partite GHZ state. To illustrate this point, consider this example with the number of users k equal to 4 and n equal to 3. To operate at capacity, the switch will always perform a swapping operation when in this type of scenario, as opposed to taking the other 2 options. Let us summarize our modeling assumptions. We model link-level entanglement generation as a Poisson process, where mu is the rate of successful entanglement generation. Quantum memory coherence times are assumed to be infinite. However, entanglement swapping only succeeds with probability Q. We can use a continuous time Markov chain to model the system. It has the state space given by the set R, where each component is a vector of dimension n-1 and each element is a non-negative integer representing the number of stored qubits for a link. Because of our protocol that bell pairs are used in entangling measurements, as soon as there are enough to generate an n-partite GHZ state, we only need to keep track of n-1 links at any given time. For the analysis, we begin with the continuous time Markov chain and uniformize it to yield a discrete time Markov chain, which we can analyze to obtain closed-form expressions for switch capacity and expected number of stored qubits when the switch is operating at capacity. However, we cannot obtain the stability conditions directly from this discrete time Markov chain. One of the most powerful and well-known tools for stability analysis of Markov chains is Foster's theorem, which states that an irreducible discrete time Markov chain is positive recurrent if and only if there exists a Lyapunov function h from the countable state space R to the reals, such that these 2 conditions hold for some finite set f and some epsilon strictly positive. These 2 conditions amount to the requirement that the drift must be negative on all but a finite subset of the state space. Let's examine why we cannot directly apply this theorem to our chain by looking at an example. This graphic represents the continuous time Markov chain for the case n equals to 3. Our state space consists of 2-dimensional non-negative vectors. From the transition diagram, we can see that there are an infinite number of states on the boundary of the chain, for which the uniformized chain would have positive drift regardless of the choice of Lyapunov function. Literature on such multidimensional Markov chains is scarce, and we could not directly apply any existing results that extend Foster's theorem to higher dimensional chains to complete the stability analysis. Instead, our strategy is to examine another discrete time Markov chain that is embedded within the first discrete time Markov chain and designed in such a way that allows us to apply Foster's theorem and obtain stability conditions for the embedded chain. Going back to the example for n equals to 3, the embedded chain would include all states from the original chain except those that are on the boundary of the original Markov chain. When the original chain traverses these boundary states, the embedded chain is frozen in time, and eventually when the original chain transitions into a non-boundary state, the embedded chain will transition into that state as well. We can apply Foster's theorem to the embedded chain and obtain conditions for its stability. We then work our way back and argued that these stability conditions also hold for the original discrete time Markov chain, and finally, that the results of all our analyses hold for the original continuous time Markov chain. Let us look at the results of our analysis. We proved that the system is stable if and only if k is greater than n. In this example, the number of users k is larger than n, which is 3, and therefore the system would be stable. When the system is stable, the capacity of the switch is given by this expression where Q is the swapping success probability, mu is the successful rate of entanglement generation at the link level, and K is the number of users. Intuitively, the product of these values is being divided by n because we need n bell pairs to generate one n-partite GHZ state. When the system is stable, the expected number of stored qubits at the switch is given by this expression. Note that this quantity approaches infinity as n approaches k. That is, the closer the switch operates to its stability condition, the more memory it needs on average. Let's look at a heat map of the log expected number of qubits. Here, the contour lines represent E of Q. The x-axis is the entanglement type, or n for n-partite GHZ state. And the y-axis is the number of links k. We can see that the memory usage becomes high near the diagonal, where n is close to k. In general, we also note that for small n, for example n less than 20, few quantum memories are required on average when the system operates at capacity. This result gives us insight on what is a reasonable number of quantum memories needed for an n-partite entanglement switch. We conclude our talk with a summary and future directions. In this talk, we introduce the n-partite entanglement switching problem, which has other applications and can be modeled as a stochastic assembly-like queuing system. We derived closed-form expressions for the capacity of a quantum switch, as well as for the expected number of stored qubits at the switch. We also performed a stability analysis of this system. Our results are a novel contribution to queuing theory. Finally, some future directions. Recall that earlier we derived an expression for the expected number of qubits stored at the switch in steady state. We believe that deriving higher order moments for the number of stored qubits may be valuable, as that would allow us to also compute the variance. In this work, we focus on an idealized scenario for quantum switch operation, but our hope is to extend the results to more realistic settings and relax some of our assumptions. For example, a more realistic system would have non-identical links, and quantum states would have non-unit fidelities. There would be a finite number of quantum memories, and they would have finite coherence times. Finally, in this work, we focused on deriving the capacity of a quantum switch, or the highest achievable rate of entanglement switching. In a real scenario, there would be user requests, possibly for different types of entangled states, and an interesting problem to study would be to explore different switching policies. This concludes our talk. Thank you for listening, and if you have any questions or comments, please do not hesitate to contact any of the authors.